Hi, everybody. This is Brian, and I wanted to present my course project for the Managing Machine Learning Projects course, part two of the specialization through Duke University on Coursera. I wanted to first start with a little bit about the opportunity of this problem space. I'm focusing on electric vehicles, or EVs, which are seeing explosive growth around the world, especially here in the United States. They reduce emissions and help transition us to a greener future. And they're exploding in popularity. But what happens when we are all driving EVs? How will our power grid keep up with the demand? So the first step is looking at the opportunity through the three questions covered in our course. The first question, is there a problem? The answer to that is yes. The growth in EV sales creates a situation in which the energy grid could potentially be overwhelmed, or at least limit the usage and effectiveness of electric vehicles. As evidence from this quote in the MIT press, if unmitigated, the evening peaks when people normally charge their EVs could require installing upwards of 20% more power generation capability over the next couple decades, according to the researchers. So we need to either rapidly expand our capacity or find better ways to improve efficiency. For the second question, can machine learning help? The answer to that is also yes. ML can help us understand the charging patterns over time of our EVs and link them to peak trends across the entire energy grid. And what's cool about this is the problem could be further simplified by just focusing on the EV charger in the home and not worrying about centralized control of charging cycles at the energy utility level. So another bit of evidence that this is something that we can look at for this. And the third question, do people care? Well, yes, both manufacturers of electric vehicles and the customers themselves are seeking ways of improving the efficiency, saving money, but also improving their overall experience with EVs. And charging infrastructure, as seen by the quote on this screen, is actually cited as one of the main reasons why other consumers are very unlikely to buy EVs. So this does seem to be a problem that people care about. So let's now dig into it using the CRISP DM process from the class. The first step is business understanding and defining the problem. I've chosen for this exercise to focus on owners of electric vehicles who have access to locations where they can charge their vehicle overnight or over a longer period of time. The most important part of this slide is highlighted, which is the problem statement. How might we leverage machine learning to optimize the electric vehicle charging at scale without creating a significant impact on our energy grid? In terms of why it matters, well, the rapidly growing EV market certainly poses risks to the scalability and long-term viability of our energy grid in order to meet rapidly rising consumption needs. If we can better manage charging behaviors of the EV market through ML systems, we can meet these needs of consumption without requiring massive investments in new power plants and other facilities for producing more electric power. How is it solved today? Well, it is true that EV owners can charge their vehicles at any time, but they still need to do a lot of manual effort today to time it correctly. And they may be without enough battery capacity to go to work or to go about their activities if they do this incorrectly. In terms of gaps in the current state, there's no automatic way to ensure that the EV is ready with the right amount of charge in time for daily commutes, but certainly you can go to a supercharger or another charging facility. However, this can decrease the overall battery life of the EV if you don't do it in the right way or you do it too often. In terms of defining success, 1.2, I decided to focus on the business impact of reducing the strain on our energy grid and our infrastructure and improving the adoption of EVs even more than is projected right now. There's also a benefit potentially from not having to rely so heavily on supercharging or spot charging because you'd be able to more efficiently plan and have enough charge by doing this charging overnight or over periods of time at home at the right times. You can see some of the constraints. There's a time constraint and also a market constraint for this type of problem space. So these are things for us to keep in mind. In terms of outcome metrics, these link directly to the business outcome I had mentioned already. I chose to focus on how could we reduce the percentage of the total charge time for an EV owner during the more expensive peak hours, which can also stretch into the evening, by timing the start of the charge cycle in the right time to avoid those peak hours. And this would also drive down the total energy cost and the percentage of the cost that is used by the EV charger. And also, working with power utilities, we could potentially increase the availability and the capacity of power plants, thus reducing peak electricity demand and driving up overall sales of EVs. In terms of the output metrics, I did feel like it would be possible to have an outlier from a different driving behavior. So you may have certain times where you're on vacation or something like that, and there could be outliers in the data set. So I wanted to focus on MAE, the mean absolute error, as the output metric. And you can also see relevant factors that I had picked through this exercise. I'm not going to read through all of these, but it covers everything from the EV charge in kilowatt hours over the course of a day, all the way to the number of EVs under active charge and the energy grid capacity and the cost per kilowatt hour. The next step is to dig into the solution I'm proposing. I feel that a machine learning powered app connected to a smart charging device could allow people to schedule or have the app automatically schedule the charging of their vehicle at the most appropriate time, perhaps overnight, so that you can actually get enough charge to go about your activities for the following day, but at a specific time so that you reduce the costs and you also reduce the strain on the network. How would we validate this solution? Well, the first step is to construct a test group of households containing electric vehicles. Then we can create interactive design mockups of this mobile app and how it connects with the EV charger, potentially using Figma or another design tool to uncover questions and consider the end-to-end user experience. Then we could use a small subset of historical data with a mocked-up model and eventually move into testing with real data from our real user group, starting first with heuristics as the model, and then eventually plugging in a simple ML model. And we'd collect app and user feedback along the way and further develop our ML system over time. In terms of design considerations, these were three main areas where we needed to select specific designs. So, cloud versus edge. I felt that cloud was probably the most suitable for this solution because latency is not a giant issue here. And reliance on internet connectivity, which many of the EVs have today anyway, is acceptable. The amount of data sent is not likely to be large or containing sensitive information about destinations or anything like that. What about the second question? For here, I chose offline learning. I felt like this was easier to implement and evaluate in production for this problem space. And the model could be retrained on a weekly schedule or a monthly schedule. There's not really any need, as I saw it, to constantly retrain the model. And the risk of making a poor prediction is not extreme in the same way that it might be for others. And I also selected batch predictions over online predictions because I didn't feel that this was a case for needing real-time predictions. Days and weeks can be treated as recurring schedules, and unlike navigation of the electric vehicle, which would probably require on-demand real-time predictions, this didn't seem like a case of that. In terms of risks in production, the biggest source of risk I saw was probably data drift. I felt that due to changing customer EV usage patterns and shifts in working from home versus going to an office, that could lead to data drift. But I also felt like there was a possibility for training serving skew especially if we train the model early on data that is not representative of a typical period of time and a typical group of EV owners. So we need to try to train on real data as early as possible. In terms of latency and concept drift, I felt that these could potentially be issues, but for the reasons stated on the slide, I didn't feel like they were most likely to be the most major sources of risk. So with that, I'm going to wrap it up. Thank you so much. We covered a lot of ground in a short amount of time, but I welcome your feedback. Take care.